Hey, we are from Group 18, and today we are going to discuss about our project classification of coffee beans using CNN. Coming to our challenges that we have observed, usually manual coffee bean classification is very time consuming and leads to a lot of errors. And ensuring this consistent bean quality is critical for flavor of the coffee made. So our goal is to develop an automated classification system using CNNs. This enhances quality control and also improves consistency in various flavor profiles. So the data set that we took was the coffee bean data set. It has a total of 1600 images of which are like training images of 1200 and test images of 400, and they're classified into different labels as dark, green, light, and medium. Each image is of the size 224 cross 224. The inputs for the model is are train and test folders, each containing the four classes, and then a CSV file, coffeebean.csv, with the metadata, file path, labels, data set, and then the class index mapping to each class of the coffee bean. The output is a predicted class label for each image, and the output is of the form softmax probability distribution across the four classes. And the final classification is based on the highest probability across these. The data exploration and visualization that we did included split visualization and class distributions. This was done using C1 count plot and also training versus testing set proportions. So as you can see, there are a total of 1600 images, out of which the train is 1200 and test is 400. And each class, dark, green, light, and medium, has 400 images each. Uh, the methodology that we used for some data preparation that we did was basically rotation, width and height shifts, zooms, and horizontal flips. And there was also pre-processing pixel normalization of rescaling 1 by 255. And then the model was pre-trained CNN ResNet 50 version 2. The base model is like the specifications of the base model that we used is on the slide. And then coming to model optimization, we used regularization and callbacks. This was mainly to like have early stopping, which restores the best weights, and also model checkpoints to save the top model by validation loss. We use the Adam optimizer with the default learning rate and sparse categorical cross entropy for multi-class labels. Uh, as previously discussed, some of the data augmentation was random rotations of plus or minus 20 degrees and validation spread of 20% to enhance generalization. Coming to the evaluation metrics and model performance, the main metrics that we took were accuracy, loss, confusion matrix, and visualization. So, coming to the confusion matrix, as you can see, it's mostly diagonal dominance of SNet 50v2. The baseline model exhibited notable confusion between light and medium classes, so this is a lot better. And then coming to loss function and learning accuracy, this is the plot of loss function with respect to epochs, which consistently decreased up to a point, and then also the learning accuracy consistency improved up to a point with respect to the epochs used. And this is our classification report for ResNet 50v2. So it shows the various parameters that we used for uh, performance analysis. So it shows precision, recall, F1 score, and also support. The weighted average for F1 score was around 99%, and all of that. So, comparing our latest model with the baseline model that was previously discussed, the test accuracy was 99.75%, validation loss was 0.0579, and the training time obviously took a lot longer, and we have a lower overfitting risk by using early stopping as discussed earlier. So some of the improvements again is an 18.5% increase in absolute accuracy gain, and also there's a dramatic reduction in misclassifications. And we can also see a higher level of feature representations from transfer learning. So finally, the results. So the accuracy is 99.75, the loss is 0.025, and there is I mean, a very good classification across the four class labels as seen in the confusion matrix, the dark green, light, and medium classes. Uh, so, coming to conclusions, Transfer learning with ResNet 50v2 significantly outperforms our previous base model CNN. The data augmentation that we used this time plus regularization yields a better generalization, and early stopping was ensured optimal stopping point without manual tuning. Future prospects, we could explore partial fine tuning of deeper blocks inside the ResNet 50v2 and also incorporate additional augmentation on images such as jitter and zoom. And we also plan to deploy a model in a lightweight inference pipeline for real time classification. Coming to prior work, none of us have any prior work, but this was our first time doing this type of project. But we have a very good understanding regarding these. The references are as follows: the Coffee Bean dataset from Kaggle, the TensorFlow KDAS documentation, and Matplotlib visualization. That's it. Thank you.